started. Hello, everyone. Thank you so much for being here. On behalf of the Environmental Finance Center Network, welcome to today's webinar on water filtration and removal processes. My name is Owen Volk from the Syracuse University Environmental Finance Center. Before we begin, we're going to go over a few logistics and then we can get started. During the webinar today, everyone will be kept on mute to ensure audio quality. If you have a question, please type it in the GoToWebinar question dialog box anytime throughout the session. We will be saving your questions for a facilitated Q&A session at the end of the presentation. After the webinar, you'll receive follow-up email that will include a link to the recording and any other information that you may need. You can also download the slides from today in the Handouts tab in the GoToWebinar control panel. This webinar has not been submitted for pre-approval of continuing education credits, but eligible attendees will receive a certificate of attendance for their personal record. To receive a certificate for this session, you must attend for the entire session and register and attend individually using your real name and unique email address. Certificates will be sent via email within 30 days of the webinar date. If you have any questions or need assistance, please contact smallsystems@syr.edu. Now for a little bit about us. The Environmental Finance Center Network provides training and technical assistance to small water and wastewater systems in all U.S. states and territories through our building technical, managerial, and finance capacity programs. If your community or utility needs assistance with drinking water or wastewater system management, please feel free to contact us through our request form, which I will be sharing shortly in the chat. One of the many ways EFCN can support your community or utility is through our free funding application support. Struggling with an infrastructure funding application, falling short on project funding, not sure where to start? EFCN is here to help. Submit a request form through the link in the chat to receive tailored support based on your project needs. And on that note, we can get started. I would like to introduce our presenter for today, Gregory Pearson, Water and Wastewater Trainer at the Great Lakes Environmental Infrastructure Center. Welcome, Greg. I will hand it over to you.
Thank you, Owen. Welcome, everyone. I'm just trying to get the screen shared here. Bear with me for a second. Can you see my first screen there, Owen? Okay, and the audio is coming through.
Looks good.
Okay, great. Well, today we're zoning in on filtration and removal processes. We're going to be starting out with some surface water concepts, and then we'll also look at some other treatment technologies that are often used in groundwater. And the first thing I want us to think about is, what are we actually removing? When we're talking about removing and filtering, what is it? In surface water, we're trying to remove turbidity, and that means that we're removing small suspended particles. And the reason we're trying to do that is because small suspended particles could include pathogens like viruses and protozoa and bacteria, and also natural organic matter. That's the acronym NOM, stands for natural organic matter, which could cause problems downstream, for example, with disinfection byproduct formation and biofilms, and can support bacterial growth downstream. In groundwater, we're typically trying to remove dissolved substances. Groundwater exists in aquifers in contact with rocks and soils, and they tend to dissolve different types of minerals, like for example, iron and manganese can be a nuisance in groundwater systems, leading to taste and color in the water. And a lot of times we'll use oxidation filtration to treat that. We could have toxic metals such as arsenic, and we might use some kind of adsorption process to remove those types of contaminants. There can be radionuclides, which there's a variety of ways. So one of the ways is co-precipitation along with the iron and manganese process, or ion exchange. And ion exchange is often used to treat hardness in water. And so we'll look at all of those concepts as we go through. But we'll start out with surface water. The surface water treatment rule specifies removal and disinfection to make sure that we are eliminating all of the hazards from pathogens in the water. But today we're just looking at the removal part. There's 4 steps generally in the surface water treatment process. The first is coagulation. And what are we doing in coagulation? We're adding coagulation chemicals that neutralize repelling charges in the particles that are in water. In flocculation, we're basically gently mixing those particles to increase the particle size. We call that flock. When the small particles in the water clump together, we call that flock. We're trying to make a larger particle that will settle or can be filtered. And then we have the sedimentation process where we allow the flock that we've grown in size and density to settle. That's one of the removal processes. And then the water that's remaining, those particles that haven't settled have to be removed through filtration. And the 2 general functions in a filter are straining and adsorption. And we'll look at those in a little bit more detail. If we want to delve down a little bit more into what kinds of solids are in surface water, there's a variety of types of particles. Of course, there's inorganic particles like silt and sand and clay from erosion. There can be natural organic matter and that's basically from decaying plant and animal matter that gets into the surface water. Surface water is not protected like groundwater, so it can experience runoff from land. It can experience debris such as plant and animal decay materials and silts, and even pollution that can easily enter the water. There can be small pieces of algae and plankton in the water. And there can be different types of pathogens in the 3 main groups: viruses, bacteria, and protozoa. And finally, there can be different types of pollution, like chemicals like PFAS and pharmaceuticals and personal care products that are in water. So there's a variety of new treatment methods that are being developed to try to remove some of those types of particles. In general, settling and filtering is a problem of particle size. If you look at this chart here, the larger particles, such as sand and fine sand, settle in a reasonable amount of time, 10 seconds and 2 minutes. And even particles that are 10 microns in size, the protozoa and algae and clay particles, could still settle in a relatively reasonable amount of time. But when you get down to the smaller particles here, you see that the settling time becomes unreasonable or impractical. So we have to do something to cause those particles to clump together so that they can be settled out. And as we get down in size, as you see that where the circled area is about between 1 micron and 1 nanometer in size, those are generally categorized as colloidal particles. They're still part of the suspended particles in the water, but they can't actually be measured in a total suspended solids test. In a suspended solids test, we filter the water through a very fine filter, and then from a known sample size of water, and then we weigh the particles that have been filtered. But these very small particles between 1 micron and 1 nanometer will not be captured in the filter. So we need another way to detect them, and we'll talk about that in a moment. But these particles are very small. 1 micron is 1,000th of a millimeter, and a nanometer is 1,000th of a micron. These are very small particles, and the reason they don't settle well has to do with the surface area to volume ratio. And so I did some calculations here, and I just used a cube. For example, a 1 centimeter cube, if it's 1 centimeter by 1 centimeter for a side, and a cube has 6 sides, the surface area is 6 centimeters squared. And the volume would be centimeter times centimeter times centimeter, 1 centimeter squared. So if you take the surface area divided by the volume, you would get a relative ratio of 6. If you do that with smaller particles, like a 1 millimeter cube, the ratio becomes 60 surface area to volume. For a micrometer cube, it becomes 60,000. And for a 1 nanometer cube, it becomes 60 million. So the surface area has a size that's 60 million times the volume. So it's just like having a really huge parachute. So it just is not going to settle unless we do something. And that something is coagulation. And we're going to talk about that in a moment. Now, we just mentioned that we can't measure those very small particles with the typical total suspended solids test because they can't be filtered. But turbidity measurement allows a method to be able to detect the presence of those very small particles. The turbidity, it's a method of measuring the intensity of light that's scattered from a sample of water. And it's measured at NTU, it's the scattered light intensity. In general, you can think of turbidity as the cloudiness of water, and the higher the turbidity is, it means we could also have the presence of pathogens and natural organic matter. The surface water treatment regulations expect us to get the turbidity down to 0.3 NTU or below, and not to exceed 1 NTU at any time. But the turbidity gives us information. It gives us information on the relative amount of total suspended solids, including those colloidals that we can't measure in any other way. And we can use it in a couple different ways. For one, we can assess the overall plant removal efficiency by looking at the in versus the out, the influent versus the effluent. And we can look at the effectiveness of the sedimentation and the filtration removal processes for each filter. For example, you can take a turbidity test after sedimentation and see how well the sedimentation basin is working. And we can take a turbidity test after each filter to see how each filter is working. And compliance is based on the combined effluent of all the filters. And that's what we're trying to get below 0.3 NTU. Turbidity meters or turbidimeters can be calibrated by using formazine. It's a chemical that can create samples that have a very accurate NTU. For example, you can see on the bottom left of your screen, you could create a 2 NTU or a 10 NTU, and you can use that to calibrate your instrument. And on the right-hand side of your screen, you can see a relative range of turbidities all the way up to 800 NTU, where it's almost opaque, and 100 NTU looks pretty cloudy. But we're trying to get it down to 0.3. That's a level at which you wouldn't be able to detect with the human eye. Here's a diagram of a turbidimeter. You see the light source on the left. In this case, it's an LED light source, which is becoming more common, and it shines through the sample. That sample could be a test tube that you're inserting into a desktop turbidimeter, or it could be a tube where it's a continuous flow of the water in the plant, and that light is coming through, and it's being scattered at a 90-degree angle to the light detector, and it's measuring the intensity of that light, and that's what we base our turbidity on. In a lot of EPA standards, you'll see a tungsten filament lamp specified. A tungsten lamp is very good because it produces a very continuous spectrum all the way from ultraviolet to infrared and it includes all the light of visible light. So it's not going to miss any of the particles in the water based on color. However, there's lots of new designs for turbidimeters using things like different types of LEDs. We're going to go to our first poll now. And it's simply asking us, what information does turbidity measurement provide?
Give it another 15 seconds. Okay, so results of the poll. Sorry. 22% said relative amount of suspended and colloidal matter in water. 1% respectively for each said the effectiveness of sedimentation and filtration process and removal efficiency of the water treatment plant, and 76% said all of the above.
Excellent job. You're a good group. And all of you are right, because it was all of the above. All these things are right. The turbidity, remember, we're measuring the intensity of the light reflected from the matter that's in the water at a 90-degree angle. And it's sensitive to even those very small colloidal particles that we normally couldn't measure. And we can take a turbidity sample after sedimentation and filtration, and we can also calculate plant efficiency. And I've included an equation here on the left. At the bottom, you take the influent turbidity minus the effluent turbidity divided by the influent and convert it to a percent. And I gave you an example in the middle of the screen here. Let's say we had turbidity in our raw water of 22 NTU, and we treated it, and we got it down to 0.25 NTU. To 22 minus 0.25 divided by 22 would give us our removal efficiency. We convert it to a percent by timesing by 100, and we see that our removal efficiency was 98.8%. Some of the ways that we can use it. In coagulation, we're going to need to add a positively charged coagulant, because not only are these particles very small and they don't want to settle because of their size and their surface area to volume ratio, but they're also negatively charged and they're repelling each other. So we add a positively charged coagulant such as alum, and that allows us to begin flocculation, which is the clumping together of these particles. And the flock particles are going to be larger and have a greater density to allow them to settle. And we see in this diagram here, we have, first of all, the negative charged particles on the left. They're all repelling each other. Then we neutralize the charge, and they begin to clump together. The coagulant begins to combine with those particles, and they clump together, and they finally are able to settle out. So that's kind of like a little summary of what we're going to be discussing here. We're going to talk about alum, which is the most popular, the most common and widely used coagulant here as an example. But these concepts do apply to more than just alum as a coagulant. But alum has two functions, or two ways that it works. The first is charge neutralization, which works at a lower pH, and that is where each individual particle is neutralized. And this works well to remove natural organic matter and small colloidal particles. The alum obtains hydroxide ions from the alkalinity in the water, and that aluminum hydroxide is what reacts reacts with the negatively charged particles to neutralize their charges and begin to form microfloc. To make it work best, you may need to adjust the pH down because it works best between 4.4 and 6 in the pH scale. And the most common acid to adjust the pH down is sulfuric acid, H2SO4. And this charge neutralization is necessary if you want to get rid of natural organic matter or total organic carbon to prevent disinfection byproducts downstream. A lot of times plants will run the pH just barely into this range so that they can take advantage of both charge neutralization and sweep coagulation. So they might run it at, like I say, a pH of 5.8. So they're getting some of both operations. When you get above pH of 6, we're mostly looking at sweep flocculation, which the alum forms a kind of a gelatinous flock, and it floats down through and captures particles as it settles. It still is effective, but it might not be as effective at neutralizing each one of those small particles. These are kind of like the charge neutralization is like the individual. There's a James Bond. He's looking for an individual particle, where the sweep flocculation is more like the blob. It's going to sweep up everything in its path. Alum has another issue. It consumes a lot of alkalinity. Like I mentioned before, it takes hydroxide ions out of the water to form aluminum hydroxide. In general, it takes about 0.5 milligrams per liter of alkalinity for every 1 milligram per liter of alum. So it reacts with the alkalinity to form aluminum hydroxide, and it uses up alkalinity. And so if you don't have enough alkalinity in the water, you could have some pH drops, you could have corrosive water, so you might need to add lime. So this shows you how alum works, but it also reveals some of the problems with alum, why you might not use alum. I'm going to give you an example of estimating the amount of alkalinity that would be required in a typical scenario here. We have a water with a pH of 7.2, has a kind of a low alkalinity, 30 milligrams per liter. And we do some testing, and we realize that the best dose is about 40 milligrams per liter of alum, and the best optimal pH is 5.8. So if we take that 40 milligrams per liter of alum and times it by 0.5, we can estimate the milligrams per liter of alkalinity that will be used up. So 40 times 0.5 is 20 milligrams per liter of alkalinity. So we started out with 30 milligrams per liter, we lose 20, and we're only left with 10 milligrams per liter. We did have sufficient alkalinity for coagulation to take place, but it's pretty low, which it would be subject to corrosivity and possibly even pH drops. If the pH drops below the working range of the coagulant, the coagulation can stop working, and it can actually the particles can actually redissolve and come apart. So we'd probably have to add some kind of alkalinity like calcium hydroxide. If we needed to lower the pH down to 5.8, we'd need to add sulfuric acid or some other acid to improve the removal of those organics through charge neutralization. So that's some of the thinking that might go on if we're trying to figure out how we're going to get this alum to work. And of course, any adjustments would have to be confirmed. You'd have to do some jar testing and try it out and monitor the plant performance. So if we had to do all that adjustment, we might want to also consider different types of coagulants. If the alum is not really practical, because we have to do so much adjustments to the water quality. And you can see an image of alum in the upper left. The Egyptians even used alum 3,000 years ago to clarify water from the river. So it's been around for a while. But some of the options are, first of all, a form of alum which is called polyaluminum chloride, or PaC. That is a form of alum that's been pre-hydrolyzed. In other words, it's already taken up the hydroxide ions that it needs, so it doesn't need to rob it from the source water. So that's an option. Another option is the ferric or iron-based coagulants. There's ferric sulfate. It can produce a denser flock than alum and works over a wider range of pH. And ferric chloride, it also works over a wide pH range. It works even in cold water. But both of the iron-based coagulants, ferric sulfate and ferric chloride, can increase corrosivity. Another option is to add polymers. You might have alum and you can decrease the dose and use polymers to improve flocculation. Polymers are long chain molecules and they have multiple attachment points, so particles can attach to it and you get a nice large flock. Polymers can be neutral, negatively charged, or positively charged, or they can have a variety of different charges that allow different types of particles to attach to them. And this is not the full list of the available coagulants. These are just some of the most common. They're developing new coagulants all the time. So if you have a supplier that you're working with, you'd want to talk with them about, what are my options. Coagulants are added in a rapid mix at the beginning of the process. I call it flash mixing. There's different methods. One is just mechanical mixing in a tank. It works for many plants. It might not be as efficient because in a tank you could have dead spots that could cause problems where some of the water is not adequately mixed. The idea is to get every particle mixed with coagulant as quickly as possible, so that you have a nice stream that you can depend on that's all mixed and it's forming flock at the same rate throughout the process. You don't want to get to the end of the process and some of the flock is still forming. You want to form the flock at the beginning so the subsequent processes can work. This is an example of a static mixer where the mixer is not actually moving. It's just a shape within the pipe, and it causes the water to change direction multiple times within the pipe. And the last example here is a mechanical inline mixer where the coagulant is being injected just upstream of the mixer in a pipe. The static and the mechanical inline mixers are probably better for making sure you have a complete mix. Although the disadvantage is you can't necessarily see inside there to see what's going on, where the mechanical mixer you could. So the mechanical mixer, it needs to have the force is mostly due to the speed and the angle of the blades, the shear force of the blades, and you need to make sure you have sufficient mixing energy and that the tanks are designed so that there's no dead spots. The next process is flocculation, and that's basically just gentle mixing, so you can grow the flock larger. Generally, we start with a higher speed and we taper off to lower and lower speeds so the flock is not damaged. In each case, we want the mixing to be fast enough to keep everything in suspension so it doesn't settle out in the flocculation basin, but not so fast that it's going to damage the flock. There's different types of mixers. This is a paddle type mixer in the lower right of your screen. And in general, you see the mixing in this image here, the mixing energy decreases as we go through the process and the flock is growing larger. And the next step is going to be sedimentation. In the sedimentation, this is our first real removal process. We're looking at between 60 to 80% removal of the turbidity if this process is working correctly. And the concept is just reduce water velocity to create the conditions so flock can settle out due to gravity. And you have in a circular tank, it flows up through the middle and flows to the outside where there's a weir. And that water has to move slowly enough so that the flock is not carried along with it, but instead settles down to the bottom to the sludge zone. You can increase the efficiency by adding plates or tubes. And as the water flows, it still has a directional flow as it's going, say, for example, from the middle of that circular tank to the outside, but it comes in contact and flows up through these plates. And when it comes in contact with a plate, the solids are or made to settle out earlier than they normally would. It increases the efficiency of the sedimentation basin. A lot of times I see it explained as it increases the surface area of the sedimentation basin, but as the particles run into these plates, they lose their velocity and they settle out. And an important equation for a sedimentation basin is the overflow rate. And the overflow rate is the flow of the water of the flow of the plant, basically, divided by the surface area of the sedimentation basin. And the whole point of this overflow rate calculation is to ensure that the very smallest particles that you want to settle out are able to settle. They have time to settle before they make it from the inlet to the outlet. And the average design rates can range from 500 to 1,000 gallons per day per square foot, or you can use gallons per minute per square foot, where it would be 0.35 to 0.7 gallons per minute per square foot. And here's the equation, the overflow rate. I'm going to just use gallons per minute per area in square foot, and we'll do an example here. And in this example, we're looking at a sedimentation basin that has a diameter of 75 feet, and the plant flow is 3,000 gallons per minute. And so if we just plug our numbers in, we'll figure out the overflow rate, but we have to figure out the area of the sedimentation basin first. And the area formula that I'm going to use is diameter times 0.785. You could also use pi r squared, where you'd take 3.14 times half of that 75. So if we calculate the area, we see the surface area is 4,415.6 square feet. And you can follow along on your calculators to make sure I'm not making a mistake here. And we already know the flow. So we're going to take the flow and divide it of 3,000 gallons per minute and divide it by 4,415.6 square feet. And we get an answer of 0.68 gallons per minute per square foot. And if we look up at our design standards, that looks like it fits within the average overflow design rates, just under that 0.7. It's toward the higher end. So keep in mind that 0.68 gallons per minute per square foot. I'm going to use that in the next slide as an example. If we convert this to gallons per day, we would just multiply it by the number of minutes in a day. 24 hours times 60 minutes is 1,440. 0.68 gallons per minute per square foot times 1440 minutes in a day gives us 979.2 gallons per day per square foot. And we see that also still fits into that design spec, which goes up between 500 and 1,000. And we can also, this last equation I put on the board, it doesn't have any numbers in it, but if we divide the gallons per minute by 7.48, we can look at the formula in terms of cubic feet per minute. And if we do that, we'd have cubic feet as our flow rate on the top per minute, and on the bottom we'd have square feet for our area. Cubic feet divided by square feet leaves just feet. So in other words, we can get a velocity out of this in feet per minute. I'm going to come back to that in a second. But let's just look here conceptually at the concept of particles needing to be able to settle out before they leave the basin. So here we have the flow that's going, say, from the end of a square rectangular sedimentation basin or from the center of a circular basin. The flow is going toward the outlet. And here we have the smallest particle that will settle here. It's settling fast enough where it can settle before the flow goes toward the outlet. And if we look at a particle that doesn't settle, it can't settle before the flow goes to the outlet. It's too slow. And we'll do a little example here. Just think about how long would it take a flock particle to settle. And let's think about a flock particle. It has to settle through 10 feet of water, and its settling rate is 0.005 feet per second. How much time would that take for the particle to settle? Well, we can take 10 foot divided by 0.005, and it will give us the number of seconds. 10 feet divided by 0.005 feet per second would take 2,000 seconds for that particle to settle. If we divide that by 60, it would take us 33.3 minutes for that particle to settle. Now, I want to do something here. I'm going to go back to that 0.68 gallon per minute and divide it by 7.48 to convert it to cubic feet per minute. And we end up with a speed of 0.0015 feet per second. So that would be the slowest particle that can settle. And this particle here is actually going 0.005 feet per second. It's actually traveling faster than the slowest particle that could settle in that previous example. So this particle, it would be able to settle because it's faster than the overflow rate. So that's kind of the concept. I hope you're all following along with that. I hope that makes sense. It's a little bit convoluted the way I explained it, but give me a, let me and myself and Owen know if that made sense to you. Now there's, do we see any confirmation, Owen?
Haven't had anything come in yet.
Uh-oh. Well, let me know. Now there's 3 basic sedimentation basin calculations that we can use. The overflow rate, the flow in gallons per minute or gallons per day divided by the area. That lets us know if we have enough time for the slowest particles to settle. The detention time is the volume divided by the flow, and that lets us know, do we have enough overall time for the water remaining in the basin for the settling to occur? And then the last one is the Weir overflow rate. It generally should not be higher than 20,000 gallons per day per foot. And that tells us about the speed of the water entering the weir. In a circular sedimentation basin, the weir is the circumference of the sedimentation basin. So we would look at the length of the weir, we'd take the flow divided by the length, and we don't want that velocity to be too high because it could create currents that could cause problems and cause solids to be lost. And this is going to be a reference slide for you to use when you want to refer back to it. And so I've included some calculations that you can use, some formulas that you can use: the area, diameter times 0.785, the volume, the equation for the volume, diameter times 0.785 times the height of the water, times 7.48 gallons per cubic foot to convert it to gallons. The weir length is pi times the diameter. And if you want to convert gallons per minute to gallons per day, you multiply by 1440. So this is a little reference slide for you to come back to if you want to refer to it. Now, we confirm.
People did say, I was just going to say, people did jump into the chat and say their understanding. So
Okay, good. Thank you. Thank you, everyone. Jar testing is how we validate or set our dosage of coagulant chemicals. You see a person here on the upper part, they're putting in different dosages of a coagulant. So you had a range of coagulant doses. So let's say you had a 5, a 10, 15, and a 20. And you might realize, okay, the 10 was the best, but not quite right. And so maybe you make a closer range. Maybe it's 8, 9, 10, 11, 12. So you're adding different coagulation dosage. You're simulating the flash mix by mixing fast with your mixers. You see the little mixing paddles at the top of that jar tester. And then you have slow mixing to simulate flocculation. And then you let it sit and settle for 30 minutes to an hour. And that simulates the sedimentation basin. And you want to see which jar has the best settling and the overall best clarity of settled water. And that's how you can adjust your dose. You can also perform jar tests to look at different effects of pH and polymers. And it's something that you can do when there's water quality changes. Like say there's a big storm and the water in the river that you're drawing from becomes very turbid. You can also use the concept of current. As you remember, we talked about turbidity in the water being negatively charged and coagulants being positively charged. Well, you would think that we'd be pretty close to a neutral charge when we combine those two things. But actually, we mostly want to run with a slightly negative charge, and this is called zeta potential because of the measurement that's used. But running slightly negative It helps us to prevent overdosing of the coagulant chemical, and actually promotes bridging together of flock particles, because now instead of being all completely satisfied with positive coagulant, they have some reason to reach out and attach to other negative and positive points with other particles. And a related instrument is called a streaming current meter, which continuously measures the current in the water, and that can give you real-time information about the overall charge in the water, so you can make quick adjustments to coagulant dosage. Just say the turbidity suddenly changes, it jumps by 15 NTU. You'd be able to see that on the current meter and make a quick adjustment. And you could even pace your dosage pump to the streaming current meter, so it would automatically adjust. So in essence, to summarize here, we're adding coagulant, we're growing flock, and we're allowing it to settle. And here's a little image of aluminum flock here, alum flock. And it's about, we're looking at a size of about 100 microns there. But what happens after sedimentation? If we removed 80% of the solids, what happened to those other 20% of the solids that didn't settle? They must be very small, and they didn't settle out. So we have to send them now to filtration. And filters are generally multiple layer. When you have a multimedia filter, the top layer will be the largest and least dense. Usually we'll use anthracite coal. The middle layer might be sized sand that's medium size. And then the bottom layer is the most dense garnet, the finest particles and the most dense particles. And this can help us in many ways, but filters can be single media or dual or multimedia like this. But media filters can actually extend the filter run and improve efficiency, because it spreads out the work of capturing the solids. The smallest particles might make it through the coal and the filtration sand, but they're captured in the garnet instead of everything being captured in the top layer, where it's all the same. Like say you just had sand, everything's captured in the top layer, the filter becomes overloaded and you have to backwash sooner. But in this case, the larger particles can be captured in the coal. And also arranging it by density helps the media to fall back into its correct order after backwashing. There's two major filtration mechanisms: straining and adsorption. Straining is just large particles can't fit between the particles of the media. And adsorption, the small particles are adhering to the media. Now the media is going to be coated with the coagulant that we fed back in the coagulation step. So that helps the adsorption. So small negatively charged particles will stick or adhere because of electrical charge. And it can be fairly complex, but you see this image at the bottom left. Some of those small particles are making it all the way down deeper in the filter bed, and they're being captured by absorption. And some of the larger flock particles are being captured by straining up higher. An example here of what a media might look like under an electron microscope. Here's a 0.5 millimeters sand media. And I'll give you a little example here of how engineers design media beds. They usually look for a bed depth to media size of a proportion of around 1200. And I'll give you an example here. We have a 0.5 millimeter sand particle in the media, and we have a filter depth of 24 inches. What's the bed to media size ratio? Well, first of all, we'd convert the 24 inches to millimeters. 24 times 25.4 millimeters per inch gives us the bed depth of 609.6. We can divide that by the 0.5 millimeter of the particle size, and we get this LD ratio of around 1219, which is pretty close to that preferred ratio of 1200. And really what we're looking at is what is the overall surface area that's available to treat. When we first start a filter, it will have a spike in turbidity, and that is called filter ripening. After backwash, we need to recoat the media with our coagulant chemical. And so we'll have a little spike of turbidity until that happens. And then that's called filter ripening. And then we'll run the filter, and we're trying to keep it under 0.3 NTU here. And we see we are until the end, which we have when we have breakthrough. And at breakthrough, we'll see the turbidity begin to rise, and we'll need to backwash. In general, filtration rates can range anywhere from 2 to 10 gallons per minute per square foot. And generally, some systems will say a max of 6 gallons, 4 to 6 gallons per minute per square foot. But this is the wide range here. And for backwash, it's faster because you're trying to expand the media. You're backwashing at 15 to 20 gallons per minute. How do you initiate backwash in a gravity filter? You're looking at maybe the depth of the water above the filter, which tells us the amount of head loss as the filter is clogging up. The water can't get through as fast. We could look at the turbidity breakthrough, or if we figure that turbidity breakthrough out, how long it takes, we can just set it on a certain run time and backwash the filter. The filtration rate is the gallons per minute per area. So here's an example. We have a filter that's 10 by 20 feet, and it has an inflow of 1,000 gallons per minute. How do we calculate the filtration rate? Well, first of all, we calculate the area. 10 by 20 gives us 200 square foot. Then we divide the flow by the area. 1,000 gallons per minute divided by 200 square foot gives us a filtration rate of 5 gallons a minute per square foot. And backwash principles for pressure filters is the same layers in this pressure filter, but usually we'll look at the differential in the pressure, the incoming pressure compared to the outlet pressure. And if that gets up to a certain difference, like say it's different, the differential is 10 PSI, we'll either have an automatic or a manual backwash. And when we backwash, we're trying to expand the media between 20 and 50%, pulls the particles apart, and we're able to wash out the dislodged particles. And then after backwash, we stop and the media falls back into place. If the backwash is too fast, you can lose media. If it's too slow, you'll have a buildup of waste products that will develop mud balls and problems in the filter. You lose filter capacity, and you can have a lot of problems. And we're going to pull 2 now. We have a gravity filter here that's 15 feet wide and 25 feet long, and it has an inflow of 1,200 gallons per minute. So I'm going to give you a chance to calculate the filtration rate in gallons per minute per square foot.
Another 15 seconds. I'm just gonna give it a few more seconds. Just seems responses are still rolling in. Okay, so 2% said 1.1 gallons per minute per feet squared. 8% said 2.3. 87% said 3.2, and then 3% said 4.5.
All right, let's look at the solution here. Here's our filter. I drew a little diagram, 15 by 25. We calculate the area. 15 times 25 equals 375 square foot. To calculate the filtration rate, we take our 1,200 gallons a minute divided by 375 square foot, and we get 3.2 gallons a minute per square foot. Great job, everyone. Let's look at some other types of treatment here. that can be, and a lot of this is groundwater treatment. So first of all, the oxidation filtration. This is also called iron and manganese removal. And so if we look at the upper right image, we can see that there's a anthracite layer and a green sand layer. And that green sand is a special sand that's coated with manganese oxide that will help to capture iron and manganese. On the bottom, you can see the oxidation filtration process where we have water coming in into a reaction vessel where the dissolved iron and manganese is converted to precipitate form, and then it can be filtered. It's a pretty simple but effective process, but this can remove iron and manganese, but it can also co-precipitate things like arsenic and radium. The only caveat to know is that manganese takes a lot longer time to oxidize than iron. Iron can oxidize in less than a minute often, but manganese can take more than 10 minutes. And here's a little example of how the green sand might be placed in the filter. And it's a special sand that's coated with manganese dioxide, and it helps to capture the iron and manganese. It has to be regenerated either continuously or periodically. And I've included some references in the reference sheet for you to learn more about that. And the oxidizer, it could be chlorine or potassium permanganate that's fed as water enters the reaction vessel. Reaction vessel gives time for the chlorine or the potassium permanganate to convert the dissolved iron and manganese to precipitate form. And so common oxidizers can be chlorine, potassium permanganate, ozone, and even just air. If you're just removing iron, sometimes you can use just aeration. You can also use the concept of oxidation in a surface water treatment plant to oxidize dissolved matter prior to the coagulation process or along with it. Ion exchange is a different kind of process. In this, we have a bed of special polymers, and the idea is that ions, it's designed for certain types of ions that you want to remove. So you have sites in the ion exchange bed that are electrically charged that coincide with the type of particle you want to remove. So if you're trying to remove a +2 calcium, you probably have a -2 connection site. And it has a limited amount of sites. Once all the sites are taken up, you have to backwash it. And if you're doing like a softener, you'll backwash it with a strong salt solution. And the sodium ions will wash out all the contaminants, and they'll recharge all those sites. But ion exchange can be used for more than just softening. It's often in home softeners to remove calcium and magnesium ions. It can also be used to deionize water. So instead of just removing positive ions, you can have a separate bed that also removes the negative ions. So they'd pass it through 2 beds to create deionized water. And there can also be special ion exchange units that remove specific contaminants such as nitrate, arsenic, fluoride, and radionuclides. And there'll be there's preferential attachment to these sites. So if you're trying to remove arsenic, arsenic can bump out a nitrate. So if it'll capture nitrate and arsenic. So if you get down to where absorption sites are full, you can actually, the arsenic can bump the nitrates down, and you can actually have nitrates pushed out into the water stream. So you have to do some pilot testing and figure out when you need to backwash. There's another technology called sorbents, and that's 2 examples of sorbents are activated alumina and iron-based sorbents. These are porous types of metals that have absorptive qualities. Absorptive means that the contaminants will adhere to them. Iron-based sorbents were talked about a lot while the arsenic rule was being adjusted down to 10 parts per billion. So that was very effective, but activated alumina is commonly used to remove things like fluoride and uranium. And you can see a picture of activated alumina on the bottom here. and it's often used to remove toxic metals. And sometimes it can be set up so the media is just a throwaway media, kind of, where you have to take it to the appropriate type of waste facility, but you just use it till it's done, or in some cases you regenerate the media. An example of an iron-based media for arsenic here, you see on the left-hand side of this diagram, arsenic 3 is a neutral form of arsenic. So they oxidize it first to convert it to a different type of arsenic, which they call arsenic 5, which has a positive charge. And then it can adhere to the absorptive iron media. And so it adheres, which is adsorbing, and then it can remove the arsenic from the drinking water. Activated carbon, it works a little bit different. It also has adsorptive properties, but it mostly works because of its massive surface area and pore structure. Just 1 gram of carbon can have around 1,000 square meters of surface area. So you have like a couple football fields worth of area in 1 little gram. So you have an image here. You see the pore sizes, and it says the particulates are getting caught in the millions of micropores in the activated charcoal or activated carbon. This can be a bed that's added to remove things like taste and odor and color in surface water. It can be in a granular form, where you would pass it through a filter, or it can be in a powdered form where you actually add it as a chemical, like you're feeding it, like adding it as a slurry to the water flow. It can be used to remove VOCs and heavy metals and pharmaceuticals, and it's also one of the recommended PFAS treatment technologies. It's created by heating it in a very high temperature in the absence of oxygen. And here's an electron microscope of activated carbon, and you can see all the pores. It creates a very complex structure where contaminants are trapped in that structure. Membrane processes are a little bit different. They force water through a membrane. In reverse osmosis, the pore size is 0.0001 microns, very small, or 0.1 nanometers. So the only thing that's making it through the pore is water, and it's leaving behind the dissolved ions. So there's a couple different concepts. The diffusion concepts are that the water has to break into smaller pieces. Instead of a bunch of water molecules being chained together, they have to go through the very small pathways through the membrane in small groups or singularly. And while the things like salts and other dissolved ions are rejected because of their size and possibly because of their charge as well. And there's an example where a salt might have a negative charge, and the negative surface of the membrane can repulse it, but also they'd be rejected because they're larger molecules. Other membrane processes are defined by their size. Microfiltration, it's kind of the same as a sand filter. You're filtering out suspended solids, and you could even have coagulation before this, but a lot of units don't have any chemical treatment in front of them. There's a microfiltration plant in the Upper Peninsula here in Michigan that's treating Lake Superior water, and there's no chemical treatment before it, and they're using microfiltration, and they're achieving a turbidity that meets the standards. As you go smaller in size, you have ultrafiltration. It has a smaller pore size, 0.01 to 0.1, and you're able to remove some small organic compounds and some viruses. If you go down to nanofiltration, you're actually getting to the point where you can remove ions like hardness ions and most viruses. So the smaller you go, the more removal you have. Diatomaceous earth is similar to activated carbon because it has a very complex structure, but it's usually fed as a slurry, and it collects on a septum. If you look at the upper part of your screen here, there's a filter that has several kind of like tubular screens. Those are septums where you feed a pre-coat feed of diatomaceous earth. It collects on those septums, and then you can feed the water, and the coated septum is now a filter, and you run that filter until the diatomaceous earth is loaded up with contaminants, and then you backwash it out. You basically just dispose of the media. The diatomaceous earth is composed of small diatoms. They're small algae that have an outer shell that's glass-like, and they're pretty small, but they range all the way up to 500 microns in size, and they come in a variety of shapes here, and they can have a surface area similar to activated carbon, but not near as large, but they can have a surface area of up to 300 square meters per gram. And the last thing we'll look at is a zoological film on a slow sand filter. As you feed raw water into this sand filter, it's a sized sand. Over time, you'll collect a layer of microorganisms that actually does the filtering. It might take a week, maybe even 2 weeks to develop this smooth deck, but then you can begin filtering. The filtering just occurs on the top layer, and when it gets clogged up, you have to actually remove that layer. And we're out of time now, and I'll leave this last poll here for you, and I'm gonna quit talking here and let Owen take over, and we can answer any questions. I'm sorry I went a little bit long, but I'll hang around for any questions that we want to answer today.
Okay, I've launched the final poll. This will go out to everyone. If you have to leave a little early, that's okay. You should still be receiving your certificate. And there will be a recording that is sent out post-webinar, so you can always watch back if you would like to see responses to questions. We're gonna keep this poll a bit shorter, so we'll give it just about 10 more seconds. Okay, so the final results for this poll, 67% said it's to convert dissolved iron and manganese to precipitate form. 7% said to convert precipitates to dissolved form, and 26% said all of the above.
Excellent. Okay, and of course we're converting the dissolved iron and manganese to precipitate form. And so if we have any questions, I'll take them. And just a little reminder of what we did cover today. For those of you that are still here, we looked at the surface water treatment processes. We looked at sedimentation and filtration calculations. We looked at some different treatment technologies from oxidation filtration, ion exchange, sorbents, membranes, activated carbon, and diatomaceous earth. And our main takeaways, sedimentation and filtration are the primary removal processes. They depend heavily on the upstream coagulation and flocculation. Turbidity provides us real-time information about the amount of suspended and colloidal matter in the water. And the treatment technologies are really dependent on the characteristics of the contaminant. For example, the contaminant charge, and the size, and the state that it's in, whether it's dissolved or not. And treatment decisions a lot of times also depend on the cost. For example, there's regulations on PFAS chemicals that are coming up. And if we look at a conversation going on in a utility, they're asking what type of treatment technology can we use? And if we look at the EPA recommendations, which I shared with you in the references, activated carbon, ion exchange, and membrane systems are all options. And there's things to consider. Activated carbon, you have to have a pretty large filter, and reverse osmosis can be pretty expensive to set up, and it has a waste stream. So those are all things we need to consider as we're looking into treatment options. Do you have any questions that I can answer now, Owen?
Yes, we do have a couple. We have about 10, and they're all pretty short, so I think we can try to work our way through them all. So the first one we got was for the turbidity meters. How does the glass/container have a known NTU value? And what is the typical uncertainty in the measurements?
Yeah, the glass does have to be calculated. It's the same concept as like if you were going to filter a sample, you would weigh the filter, so you could subtract off the filter, and it's the same concept with the glass. Um, the There are turbidimeters, I think, that can measure through a stream of water without the glass, which would be a benefit. The degree of error, I'd have to look into that a little bit closer. That's a good question. In other words, like at what level is non-detect? Can we detect a difference between 0.01 and 0.02? I'm not exactly sure about that. I'll do some research and respond in the follow-up email.
Perfect. We do have more questions rolling in, so we just so everyone knows, we probably won't be getting through all of them. I will send them over to Greg for responses and include that in the follow-up email. So the next question we got was, could the use of polymers increase the microplastics in drinking water?
Yes, yes. Well, I mean, the use of polymers, no, it can help to, it could help to remove microplastics, though, because you're capturing those in the filter. They're not going to make it into the water stream typically. However, some some coagulant chemicals can make it into the water. Those can be dissolved, where a polymer typically wouldn't be something that would dissolve.
Perfect. Next question was, is allium sludge less dense and fluffy?
Yes, it is a little less dense and fluffy. That's exactly correct. And some of the iron-based coagulants make a more dense sludge, which can actually cause the other type of problem, which can make it a little bit more difficult to remove the sludge in the solids handling.
Perfect. Someone was looking back at the equation. They were wondering where the 0.785 comes from.
Well, that's a good question. When we typically do area, we do pi r squared. If you wanted to do pi and use diameter instead of r, you would have pi times d over 2. Diameter divided by 2 is an r. So you'd have pi times d over 2 times d over 2, which would give you pi times d squared times a quarter. So a quarter times pi, if you just use 3.14, 1/4 of that is 0.785. So that's where it comes from.
Okay, perfect. Just give me 1 second here. I'm just trying to make sure we have all these questions collected. Next, someone was wondering, what does the coating of the filter media with coagulant do? What benefits are offered by this?
Oh, the coagulant coating the media allows the media to adsorb. So you have a particle of sand and it's coated with alum, for example. That particle is now positively charged, and a negative turbidity particle comes along, and it's going to stick to it because of its electrical charge. So we removed all of the large particles in sedimentation, but when we go to filtration, the water that comes out of the sedimentation basin is those very small particles that wouldn't settle. So we need to have adsorption to make sure those particles don't make it through between the particles, so that coating creates an electrostatic way of capturing those small particles.
Perfect. I think we'll do one more, and then we'll do 2 more, and then we'll get all these other questions answered in the follow-up email. Someone was wondering, can you explain what head loss is?
Yeah, head loss is when, let me explain it this way. When the gravity filter gets clogged up, the water can't make it through the filter. It's kind of a not the best term, but the water can't make it through the filter because it's clogged up, and so there's a pressure differential. The pressure on of the water trying to push through due to gravity is not sufficient to move through the filter anymore because it's clogged, and so the pressure going out is the flow and the pressure of the water going out the filter is lower, so you have a differential. But it just means the filter is clogged up and water can't get through it, so it's building up on the top of the filter. Instead of being 1 foot deep, it's now 1.5 foot deep trying to get through the filter.
Okay, perfect. And then for the final question, I think that was the final question. We did just hit the one on the metal organic frameworks now. Yeah, I think that was the last question. So we will get all the rest of these responded to within the follow-up email. So we can wrap up for today. A huge thank you to Greg for sharing his expertise with us today. Following the webinar, you will receive a follow-up email with the slides from today and a link to the recording. We also ask that you complete the webinar evaluation following the webinar so that you can let us know your thoughts on today's session, as this helps us plan for future webinars on topics that are important to you. Thank you again, and we hope to see you at future EFCN events.
Thank you, everyone. Thank you, Owen.
No problem. Have a great day, everyone.